Yeah, camps on everyone. Let's start off. That last class we have done this. L1, this is V, this is R, this is L2. The switch is initially connected to A for a long time and then flip to B. Then find the current in the circuit. So now you're connecting an inductor to an inductor. How this camps on? So we have seen something like this in LR discharging circuit where you connected an inductor to a resistor. Remember last time we discussed what does an inductor try to do? Inductors try to oppose the change in current. So if you look at the circuit here, so initially the current in the circuit is, let's say capital I. I is equal to V by R. Now the moment you close the switch, the inductor L1 says, boss, I don't want the current to change. I want to have I. Inductor L2 will say, I also don't want to change the current. I want zero. You're getting what is happening? Both are trying to fight now. So for a moment, the currents don't establish. So this guy will have a current I and this guy will have a zero current. This is an intermediate stage. These things always happen, when you connect a battery to a resistor, you won't get immediately current. There's a small delay in some nanoseconds. It takes time. We always study the steady state. So then eventually what will happen? Both of them will try to fight. Now this current will try to go through L2. So you'll start getting sparks and everything. Eventually they'll establish some kind of an equilibrium. This current will become some I common and this current will become some I common. Now if you try to apply Kirchhoff's loop law in this, minus, wait, Let me take it like this. Let this current be some I1, let this current be some I2. So currents are not same. They are trying to establish an equilibrium. And this will be minus L1 di1 by dt minus L2 di2 by dt is equal to 0. Minus L1 integral di1. This will be L2 integral di2. If you look at the current, this current goes from capital I to I common, and this current goes from 0 to I common. You get I common is equal to L1 I by L1 plus L2. So both the both the inductors, right, will find, and eventually they'll establish at this value. And during this process, you also get some heat. Heat will be E initial minus E final. So initial energy will be half L1 I square. That is energy in the initial inductor minus half L1 plus L2 I common square. So if you subtract them, that will be the heat produced. So whenever you do something like this, you put two inductors and try to suddenly switch or close the switch, right? You'll start getting a lot of sparks. So a resistor would be an LR discharging circuit. It will decrease gradually. But if you put an inductor, they would fight something of this sort. And if you look at the result, right, it gives you something here. Remember what is L into I? Flux. So if you look at here, when you do L into di, this is basically change in flux. So if you see the whole question, it gives you something of this sort. It gives you a feeling as if, flux is conserved. Remember, there is no concept like that in physics. Yeah, but it will help you in the exam. It will give you the answer faster. If you look at the initial flux is equal to final flux, this looks like L1 into I. The final flux will be L1 I common plus L2 into I common. There, at least that is how the final answer looks like. Clear with this? So technically, even though inductors are non-dissipating elements, but if you let them fight with each other, this is what is going to happen. Both the inductors will say we don't want to change the current. So someone has to come down. So there will be a compromise. Clear with this? So we have seen last time what happens if you keep an inductor and a resistor. This is what will happen if you have an inductor and an inductor. What happens if we keep an inductor and a capacitor? We call this thing LC oscillations. This can be a theory question, everything. So we'll do it as a problem. Let's say we have a capacitor. We have an inductor with a switch. Let's say this is plus Q and this is minus Q, and the switch is closed at t is equal to 0. Find the charge and the current at time t. Actually, if you can find charge, you'll get current also. Let's find the charge at time t. I can ask you a lot of things. Find the energy stored, current, energy in the inductor, magnetic field, all that stuff. How do we start this? I'll just give an idea. Always, when you see circuit, what you do, always start with an intermediate stage. Let the charge on the capacitor be small q minus q. Let the current be I. I is equal to minus dq by dt. Minus because the charge is decreasing. You can do that, or better, let charge q flow from here. This will be q minus q and minus of q minus q. Same story, doesn't matter. You can say I is dq by dt. Same thing. So if you're assuming small q, then take minus because it is decreasing. So here also we can do the same thing. Say this will be like q minus q by dt. And minus sign because the charge is decreasing. So this will become dq by dt. So depending on how you want to use it. So stick to one convention. If charge is going to the plate, then q will increase. So current is positive. The charge is coming from the plate, then it is negative. Then apply Kirchhoff's law inside this. I'll go from negative to positive plate. So this is q minus q by c minus L di by dt. And then you get L d square by dq by dt square is equal to, take out minus common, you'll end up with q minus q by c. This looks like d square q by dt square is equal to 1 by LC q minus q. Clear with this? This looks like your SHM equation. D square x by dt square is equal to minus omega square x minus x mean. The general solution for this will be x minus x mean is equal to x naught sine omega t. So this will be q minus q is equal to q naught sine omega t plus phi. At t is equal to 0, q is equal to q. So this will be 0 is equal to q naught sine phi. So phi is 0. At t0, current is also 0. So I will be dq by dt, which will be q naught omega cos omega t. Did I miss? At t0, unnecessarily made it more complex. Q naught cos omega t. I got q naught 0. I messed up something. What did I mess up? Q is equal to q naught cos omega t. Hmm. It will be q plus q naught sine omega t. Where am I going wrong? I think I should have just taken small q on the charge plate. That q naught should come out to be, if current is 0, this will be q naught omega 0. I'm getting q naught is 0. Yeah, that would be easy, Vihan, but what is wrong with this? You can tell me what I went wrong here. At T0, Q is 0? Nee, re. At T0, capacitor is full, na? At T0, Q is Q. That is
नहीं लेकिन Q minus Q is the charge on the capacitor at time t, right?
okay.
I think
Nee, I'm getting Q naught 0, na? That is the problem. I'm not sure what I did wrong here. Okay, we'll just take it as small q and minus q. That would have been easy. I should get with this unless I'm goofing up somewhere. This will be q by c is equal to, you will get straightforward here. Previous one should have got it. So T0, Q is equal to Q. I think the Q naught is Q only, simply. That's the maximum charge actually. Somewhere we goofed up. At T0, Q minus Q was 0. सही बोल रहे हो. At T Q minus, okay, Puruja, yeah, I got what you're saying. I should have taken Q minus Q as 0. The previous thing was right. ठीक है, I goofed up anyway, so this also will get it. This will be Q sine omega t plus 90. You get Q cos omega t. You want current minus dq by dt. This will be Q omega sine omega t. This will actually give you the maximum current, which is Q omega. Clear with this? This is also fine. Yeah, the previous one was right. Initially, Q minus Q was capital Q. Small q must have been 0. That was a mistake I was doing. There, you can get the maximum current like this. There is another easy way to get the maximum current. You can conserve energy. The total energy in the capacitor, energy is conserved here. So basically, this would be an SHM. That's the reason, if you see, we call it LC oscillations. It's oscillating between, the electric fields and the magnetic fields. So this, you can compare this. Look at the picture, how it looks. So this is the scenario at t is equal to 0. This is the scenario at t by 4. This is the scenario at t by 2. This is the scenario at 3t by 4. And 0, this is the scenario plus q and minus q. So there's an electric field between the plates. Current I is 0. So the magnetic field is 0. Then at t by 4, the entire capacitor becomes empty. Current becomes maximum. So all the electric field is converted into magnetic field. Then this becomes plus q and minus q. So the field will reverse direction. Again, current becomes 0. Magnetic field becomes 0. Then again, this becomes empty. This time the current is reverse direction. I max. Now the magnetic field will be in this direction. And again at 2t, you come back to the initial state. So if you actually think about this thing kind of looks like a spring and a block. So initially the spring is in natural length. The velocity is at Vmax. And you can look at the comparison here, say. We know Q is equal to CV. We know momentum is equal to mv. We know energy in the capacitor is half CV square. We know energy of the block is half mv square. Can you see the resemblance? Mathematically, they look the same. If you're going to say charges, Q is equal to CV and P is equal to mv, Max will simply say you just change the variables. Max doesn't care what you want to call, isn't it? The functions look similar. So here the speed is like the charge on the capacitor. So here the block will reach the extreme position and so on. So you can actually compare this with the spring block system. Clear with this? So if you want to find maximum in a current, you can actually do this. Energy in a capacitor is equal to energy in the inductor. So all the energy in the capacitor, when it goes into the inductor, you get maximum current. You can actually conserve energy. It's a proper mains level question. Find the maximum current. And so there's no need to do all this stuff. You can directly conserve energy. Clear with this? Let's see something like this. Something a little more variation. What if you have two capacitors and an inductor? C, 2C and L. Plus Q, minus Q, 0 and 0. Find maximum current. And charge on the capacitors at time period. Actually, charge on the capacitors, right? If I ask you charge, you have to find everything. Let's get this. This is a better variation than the previous one. How do we approach this? Same story. Always start with the intermediate stage. Let Q charge go from here. This will be Q minus Q. This will be Q minus Q. The Q will flow here and come here. This will be Q and this is minus Q. If you remember, we did this thing in capacitors. When you have multiple capacitors, you always assume one capacitor is giving charge and the others are taking. Now write Kirchhoff's law. Right, what a minute. Once you got the equation, it is done. It's all math after that. So what is the equation? Q minus Q by C minus L di by dt minus Q by 2C is equal to 0. I is nothing but dq by dt square. There. For this, the general equation will be Q minus Q mean Q naught sine omega t plus phi. At t0, small q was 0. It is on this 2C capacitor that was empty. Something like this would have come in the previous case also. So from there, we'll get Q naught is equal to minus 2Q by 3. Therefore, Q will be 2Q by 3 minus Q naught cos omega t. 2Q by 3. If I put t0, I'm getting 0. Yeah. There, that's your small q. I think once you got this, you will get everything. You'll get the charge on the other plate. You will get the current, I is dq by dt. You can get the maximum current. Maximum current is what? Just differentiated to q by 3 omega. You'll get everything. Clear this? So if you try to compare this with the spring block, how does this look like? Remember this problem? Find the maximum compression. So again, if you see the resemblance, F is equal to Kx. Flux is equal to Li. Energy in the spring is half Kx square. Energy in the inductor is half Li square. So if you see, velocity it will be similar to potential and current is similar to elongation. Similar to. You can't say they're equal types. So I hope you remember here. When do we get maximum elongation? Max elongation occurs when both the blocks have same velocity. So I can use the same statement here and say maximum current occurs when you have same potential difference. And just showing the resemblance. That means if I just want to solve for the maximum current, writing equations is easy, but you can handle this. C into C and L. So for maximum potential, the charge should vary in the ratio of Q by 3. This is another question I can ask you. What is the charges on the capacitors when there is a maximum current? At this point, current is max. So you can say Q square by 2C, the initial energy, Q by 3 whole square by 2C, 2Q by 3 whole square by 2 times 2C, plus half L max square. Do you guys remember how to find the time period for this? 2 pi root over mu by K. Mu is the reduced mass. Don't forget those formulas. Saves you time in mains. Clear with this? So there you can play around like that with LC oscillations. You can even keep 2 inductors, 1 capacitor. So if you have an inductor and a capacitor, right? Capacitor is more than happy. Like, it will take the charge, it will absorb the charge, it will give the charge. So it does not fight with the inductor. It will let inductor do whatever it wants and capacitor will be there to take the energy. So that's why you have an LC oscillation. In this case, you won't have any dissipation. And you can clearly see how electric field converts to magnetic field and magnetic fields converts to electric field. And this is how you make, your oscillating circuit. When you're sending a signal, this is what you're actually doing. If you change your capacitance and LNC, you can generate a certain frequency of signals. So this is what you actually do in communications. So that is one thing about LC. Next thing, we have something called mutual inductance. Last time we saw self-inductance, which was opposition to the change in flux created by your own system. Mutual inductance is the opposition to the change in flux. See, one thing, every system will oppose the change in flux. If it is due to yourself, we call it self-inductance. If it is due to someone else from outside, we call it mutual inductance. Upon the change in flux induced due to another system. So let's say you have two coils. If you send current I, this will generate magnetic field. B1. So flux in the second coil will be integral the magnetic field due to the first coil dot area due to the second coil. Now, we can't calculate this value exactly, but one thing I'm sure, this will be proportional to I1. Because more current you send, you get more magnetic field and the flux will increase more. So from here we can say the coil flux on 2 will be mutual inductance, we call it M21 into I. If you do the reverse, now if you send the current in coil 2, and if you try to calculate the flux on coil 1, this will be integral B2 dot dA1. This is proportional to I2. So here flux on coil 1 will be M12 into I2. So that means if you make both the currents same, right? And one thing we'll observe. So think of like this, when the lines are going from here to here, right? The number of lines passing through both the coils is same. So that means the flux in both the coils will be same. And if you make the currents also same, you will observe, we can actually prove this, with an experiments and all that, M12 becomes equal to M21. We just replace them with one constant. We call it mutual inductance. So it doesn't matter in which coil you send the current, the flux generated will be same. So it gives you a pretty interesting result. So let me put that in a more usable form. What this thing says is, if you have two coils, flux in any one coil will be equal to mutual inductance M into the current in the other coil. This will give you pretty, it helps you to solve certain questions where you cannot actually calculate flux in a direct way. Let me show you with an example. There, mutual inductance technically is that only. If you remember in self-inductance, flux was Li, here flux is Mi. So let me show you with this an example. So this is one of the PYQ. Standard questions, there are 3 standard questions in mutual inductance for mains level. Advanced level, you have a different stuff, you will see that. But look at this question. So we have a big coil here, radius R. There is a small coil, radius small r. And the distance is x. And the question was this. Current I was sent in the small coil. Find the flux in the big coil. And find the mutual inductance. That was the question. Now, technically speaking, if you actually try to find, this is what you will notice. Due to the small coil, the field lines are messed up. We don't know how to find the magnetic field for this. We cannot find B bar. We can only find B bar on the axial line, if you remember. This is where mutual inductance helps. Now, the mutual inductance says it doesn't matter in which current, which coil you send the current, the flux will be same. So these kind of questions, they expect to do like this. You go for the reverse. You will say, let the current be in this coil, same current. And we know the magnetic field ka formula, which is mu naught I R square by 2 into R square plus X square whole power 3 by 2. Since the coil is much, much smaller, I can assume the field is almost constant. And this is the catch. This is how they'll always ask questions. They'll give you current in such a way you can't find the flux. But when you take the current on the other coil, suddenly you can find the flux. We can assume B bar is constant. And then we'll say flux is equal to BA. mu naught I r square small r square by 2 into r square. Perfect. This is equal to mi. I gets cancelled, you get the mutual inductance. So the mutual inductance depends only on the distance between them and the geometrical shapes and everything. Clear with this? So the questions, the way they will frame will be like you won't be able to solve that. But if you take the current in the other coil, suddenly you can solve. Let me show you one more example. This we have done before, the starting part of the chapter flux. We have an infinite wire and we have a ring. Again, this is the same story. Current I is flowing in the circular ring. Find the flux in the infinite wire. And also find M, mutual inductance. Anyone remember the result? This was the question. Mu naught IR. This is how they'll frame a question. They'll put in terms of mutual inductance. याद आया? 3B था, 2B. So we do the question the reverse way. Let the current flow in the infinite wire. Then we know flux is mu naught IR. This is equal to Mi. हो गया one step में. Yeah. You can take that square loop also. Square loop and that wire if you remember. You can play with that also. That is another standard model. So this is one standard model, ring and ring. Second standard model is infinite wire and a square loop. The third one, let's do that as a question. Coaxial solenoids. Let's say we have a small solenoid and then enclosed by a bigger one. Infinite. Let this radius be R1, let this radius be R2, let this be into turns per unit length. This is N1, this is L. L is much greater than R1, R2. Find mutual inductance of the system. That means if you send current in one coil, how much will it interact with the other one? This is your standard question. Third one. Let's see how will you do this. Find the mutual inductance. Just to give you the steps. Whenever they ask you to find mutual inductance, step one, assume current in any coil you want. Whichever you feel is convenient. Step two, calculate the flux in the second coil. Step three, write flux is equal to Mi. So the I term will cancel off every time and you'll end up with this. So how we do this? You can send the current in any one. I'll send the current in the outer one. Then the magnetic field will be mu naught into I. See, if you send the current in the inner one, then the field will be only from 0 to R1, isn't it? Field outside the solenoid is 0. Then the flux in the small coil, 1 will be the magnetic field number of turns B into pi R1 square. It doesn't matter where you take, you'll get the same thing. This will be N1 into L. This will be mu naught N2I into pi R1 square. This is equal to Mi. Standard result, definitely remember this. Mu naught N1 into pi R square. It depends only on the inner radius. It doesn't depend on R2. If you have taken the current in the inner one, then what will be the magnetic field? Mu naught N1I. But this field is only present from up to R1. That means from R1 to R2, there is no flux. Then the number of turns will be N2L. Mu naught N1I. Area will still be pi R1 square. Are you getting it? There is no magnetic field from R1 to R2 if you send current in the inner coil. So the answer will come out to be the same. It doesn't matter where you take the current. Clear with this? This is one way. Now, another way of asking questions. Let's say we have two hollow cylinders. Infinite hollow coaxial cylinders. This radius is R1, this radius is R2. Current is coming out of the inner cylinder, it is going to infinity. So it goes to infinity, it takes a turn and comes back here. So if you see the top view, current is coming out here. Current is going here. Now, if you take both of them as one system, you take the inner and the outer one as one cylinder, where you can assume the current is turning at infinity, then we call it self-inductance because everything is one system. If we take both of them as separate, we can call it mutual inductance. So depending on what is your system, the same thing you can call self or mutual. Getting it? So we can assume the current turns at infinity. So it's a loop basically. Find self-inductance per unit length. Toroid. This is not toroid, right? Toroid looks like what? It's like your donut ka shape, na? And the coils are curved around. This is straight wires, isn't it? Infinite cylinders like straight wires. Let me show you. See, there are two ways you can approach this. But first of all, before that, you need to find the magnetic field inside. Do you guys remember the magnetic field inside? The magnetic field inside a hollow cylinder is 0. So it will be 0 for R less than R1. For outside, it behaves like an infinite wire, mu naught I by 2 pi R. This is between R2 and R1. And once you go outside, again it is 0 because both the currents are opposite, they'll cancel out. So the magnetic field is present only between R1 and R2. Is that clear, everyone? There is no field outside and there's no field inside R1. So if you look at the top view, this is how the field looks, concentric circles. Now you can handle this two ways. One, you can actually take an element like this and you can calculate the flux here. So you have to integrate for each section. Or I don't like that generally because sometimes you get confused like how to take elements here, how to take the flux and all. So the best way would be you have one more place where you get this self-inductance, energy. Take a thin cylinder. We have already done this last class. Let this radius be R and thickness be dr. So the volume for this thing will be 2 pi R L dr. Then we can use the formula dE will be 1 by 2 mu naught B square dV. So I can find the total energy stored, which will be integral 1 by 2 mu naught square I square by 4 pi square R square 2 pi R L dr. Limits will go from R1 to R2. From here you will get 2 will cancel. 1 mu naught will cancel. You will end up with mu naught I square by pi L. That will be ln R2 by R1. There is a 4 also. Done. Once you get energy, what is the energy of an inductance? Half Li square, isn't it? That's it. So from here you get L value. L will be mu naught by 4 pi, mu naught by 2 pi ln R2 by R1. There. That's one way to handle this. Energy is a savior. Because in case of a flux, you have to start thinking, how should I take the area? If you take surface area, you will get flux 0, isn't it? Clear with this? So this is one way of solving using energy. Let me show you one more like this. What if we have to infinite plates? Let this be A, let this be B. You can take B much greater than A. So current is flowing like this, and it returns from infinity like this. The side view will look like this sort. Find the self-inductance per unit length. All these questions will ask per unit length because if you take an infinite length, you get infinite energy. So A is the distance between them, B is the thing. Everyone remembers the formula for infinite heat, magnetic field? Mu naught K by 2, right? Let's get this. Now this was actually easy. There's no need to integrate here. You'll get a B bar constant. Hope you remember how to get the direction. Take any one wire and see how is the field. Mu naught K by 2. Anyway, direction really won't matter. So this also will be mu naught K by 2. K is the current per unit width. Take this as length L. So here the energy stored will be 1 by 2 mu naught. B will be mu naught K square. Volume will be, it's a cuboid LAB. This is equal to half Li square. This will be mu naught by 2. K will be I square by B square LAB. I square cancels, 2 will cancel. We'll get L is equal to mu naught A by B. There, that's your answer. Clear this. This is how they can ask you self-inductance of other systems. What you have seen so far is only solenoid, but you can create other systems like this. All clear with this? Any doubts on this? Next thing, combination of inductors. What happens if you put multiple inductors together? Now these inductors, right, unlike resistors and capacitors, these are a little messed up. They do interact with each other. If you keep a two resistors side by side, they don't interfere with each other's generally. So resistance doesn't get affected. Even capacitors don't interact with each other. But inductors are different. If you neglect mutual induction, then that would be straightforward. So if you keep two inductors in series, L1 and L2, L equivalent will be L1 plus L2, just like your regular one, just like resistors. There. But once you bring mutual inductance into the picture, things get different. So let's see that after the break. Take a break, come back by 9:38. Any doubts so far?
So,
Yeah.
so in the two cylinders inside of each other, one,
Hmm.
that I didn't get how it's acting as a inductor, like that much. Like,
Why can't it be inductor? What is the problem?
instead, I'm not seeing that loop kind of a thing.
There it is an
or-
infinite thing. So it's going to infinity and coming back. What is the problem?
So this is like kind of like two loops.
It is just inner wire, outer wire. That's it. Current goes from inside and comes from outside. Think of like a fountain, right? Water comes from the center and comes out from the other outside.
This is like kind of like a toroid, basically.
Can't say it's a toroid, but
Cross section of the toroid.
it just goes from the
But
center like a fountain. It's like,
yes, sir.
but there's a whole cylinder there. So
Yeah, got it. Thank you, sir.
chalo, come back in 5 minutes. Yeah, let's start off. What happens with mutual inductance? Let's see series. In this also there are two cases. Supporting. Meaning, let's say we take two coils. Let the mutual inductance be M. Now see what happens. Due to the current in the first coil, so these field lines will enter the L2 coil. Like I said, so the coil 1 ka flux is entering the coil 2. So if I write the flux in first coil, it will be L1, I1. This is your self-inductance. This is the flux because the current in your coil plus mutual inductance, which is M into I2. This is the flux due to the second coil on yourself. But I1 is equal to I2 here because they're in series. Therefore, flux on the first coil will be L1 plus M into I2. Similarly, when I write for the second coil, self-inductance is L2, I2 plus mutual inductance is M I1. Are you getting it? So till now we used to write flux is equal to Li. Now you'll write Li plus Mi2. You have to include the flux due to the other guy. Same story here. Current is same. So this will become L2 plus M into I. So when you want to replace this with one inductor L equivalent, so flux will be L equivalent into I. So phi1 plus phi2. We get L equivalent will be L1 plus L2 plus 2M. Where M is the mutual inductance. Like M tells you how much both the coils interact. The same thing, if I put the coils in the opposite direction, then it will become subtracting. The mutual inductance will cancel the flux. This we never had it in capacitors and in the resistors. So here one coil is supporting the other coil, and the overall system mutual inductance increases. If I take case 2, opposing, so there in the orientation is reversed. Meaning the coil is this way, the coil is this way. Can you see the difference between both the coils? So here the coil rotation will reverse here. So this magnetic field will be this way, whereas this magnetic field will be this way. So here now both the fields are fighting. This M will be given. So L equivalent will be L1 plus L2 minus 2M. So that orientation will matter. Are the coils supporting each other or opposing each other? Accordingly, your self-inductance will change. Clear with this? The parallel is the most messed up one. Technically, we don't have parallel in the portion, but mains method they'll never touch that. Even this thing they won't touch in mains, right? But I will write the equations. You can solve it and get the result. So it can be asked as a paragraph question. In parallel, again, if you take supporting, here it will be reversed, opposite sense. So here when the current I1 is flowing, the field lines are going down. So here the field lines are like this. So if you see these field lines will enter into this and red field lines will enter into this, both are supporting each other. So here you need to have an opposite sense of rotation. And now you want to replace them with one single thing. Now listen to the equations carefully. In the first one, if you look at the potential difference V1, L1 di1 by dt, this is due to your self-inductance, plus M di2 by dt, this is due to the mutual inductance. So each coil will generate an EMF which will depend on both. Similarly, V2 will be L2 di2 by dt plus M di1 by dt. Since they're in parallel, V1 is equal to V2. And capital I is equal to I1 plus I2. And V1 is equal to V2 is equal to L equivalent di by dt. There, you get 4 equations like this. Take it out. Take out the equations. Then you have to do little plus and minus and solve this. I did this last time. You will get it. It's like 1 page, 1.5 page of solution. Check it out. The final answer will turn out to be L equivalent will be L1, L2 minus M square by L1 plus L2 minus 2M. This is how the formula will turn out to be. Complex one, but yeah. So these are the 4 equations. You can solve this. Start from here, differentiate this, you will get di1 by dt, di2 by dt, and then you can replace these things. You'll get a relation from there, you can figure it out. Eliminate, this I1, I2, and a capital I from the equations. I'll leave it to you that you can figure it out. But this thing, the formula also, right? It's not a standard formula. You should take the other case, but are the 4 equations clear, everyone? The most important is this, how to write this single equation. It's not LdI by dt anymore. So if you take the opposing case, they'll be in the same sense of rotation. We get L equivalent will be L1, L2 minus M square. Numerator will be same, denominator will change, L1 plus L2 plus 2M. Here we have this quantity L1, L2 minus M square is always greater than equal to 0. So we define a quantity called K, which is M by root L1, L2. This is called coupling factor. So what K ka value tells us is, it tells us how much flux from one coil will enter into the another coil. If K is equal to 1, meaning the fluxes will enter perfectly, meaning all the flux from one will enter into the other one. Yeah, that's about the parallel thing. Clear with this? Great. So we know energy of an inductor is half Li square. Then what if you have a coupling circuit? If you have mutual inductance, then energy won't be the same. But technically, till this point, right, we have done with the chapter. The mains part is done. Now, whatever you're going to do now will be on the border of, the portion, basically. Mostly all this will be advanced stuff. Most of the time, these things will be, they'll ask you in a paragraph and then they'll ask you the stuff. So let's see. Energy in a coupled circuit. Coupled meaning they're interacting with each other. Let's say we have 2 coils here. I1, I2, L1, L2, M is the mutual inductance. Now in the first coil, the voltage V1 will be again same story, L1 di1 by dt plus M di2 by dt. We know energy stored in the system is nothing but power into time. And power is nothing but voltage into current. So this will be V1, I1 dt integral V2 I2 dt. When you substitute that, you will notice you will get up with L1 I1 di1 plus M I1 di2 L2 I2 di2 plus M I2 di1. This would be half L1 I1 square. There's energy in the first inductor, half L2 I2 square. That is also great. This will be M I1 di2 plus I2 di1. Did anyone notice what is this? Perfect differential. So we get the total energy will be half L1 I1 square. So this is your standard inductor energy. So this is the energy stored inside the inductor. So this extra term which we got Mi1, I2, that's your interactional energy. That is energy stored because of interaction between both the systems. So in capacitors, if you remember, we call this thing self-energy. Self-inductance, self-energy. This is your interaction energy. This is the energy that comes because both the coils are interacting. Clear with this, everyone? Quite a useful one. So whenever you have two systems and if there's a mutual inductance between them, this is the energy formula we have to use. You just can't use half Li square anymore. If the coils are not interacting, then M is 0, then fine. You get back your old formulas again. Clear with this? Then we did something similar to this in electrostatics. Let me show you that. But any doubts on this page? Again, not difficult, but slightly out of the box, but still within our range. So this itself they can ask you. This itself is a direct question. Another way they can ask you, frame this question. We know the total energy is nothing but 1 by 2 mu naught B square dV. This can be written as 1 by 2 mu naught B1 bar plus B2 bar square dV. If you expand this, you will get 1 by 2 mu naught B1 square dV plus integral 1 by 2 mu naught B2 square dV plus 2 times 1 by 2 mu naught B1 bar dot B2 bar dV. किसी को याद है? There was a question like this. Find E1 bar dot E2 bar dV. So they can frame a question of that sort. Find B1 dot B dot integral B1 dot B dot dV. Now, if you look at these terms here, this is half L1 I1 square. This is half L2 I2 square. And this is M I1 I2. Clear with that? So just like electric field is a form of energy, even the magnetic field is a form of energy. Yeah, we did this in spherical capacitors. So they'll frame that question. They'll ask you, what is integral B1 bar dot B2 bar dV? And that would be mu naught M I1 I2. This is another way of playing around with magnetic field. They'll say there are two inductors generating field B1 and B2. Mutual inductance between them is M. What is integral B1 dot B1 bar dot B2 bar dV? So you need to understand that B1 dot B2 will come from interaction energy, and interaction energy is this term, half Li1 square L2 I2 square M1 I2. You can connect things like this with the field and the energies. Clear with this? Same thing we saw in electrostatics, the capacitors. Now this you can take it higher. You can combine this with something else. Superconductors. Now we'll not get too deep into this how superconductor works, what is that and everything. In terms of flux, there is one important thing about a superconductor. And again, generally if they ask you this, they will give you a paragraph to explain. So the one property we're interested, right, in superconductors, once you generate the flux inside, the flux will remain constant. Yeah, until unless you put one more battery to oppose it. In superconductors, magnetic flux it remains constant. Looks pretty straightforward statement, but it tells you something. That means if you try to mess up the system externally without touching the superconductor, the superconductors will do something in order to maintain that. So current in superconductors, let me give an example. Let's say we have a superconducting ring. You take a magnet and put it in front of it. And let's say inside the current is 0. So initially the superconductor has no current, but there's a magnet outside, so there is some flux. Let phi be the flux due to the magnet. Now what you did, if the magnet is removed, let's say you just don't touch the coil, keep the coil there only, and just move the magnet from there to infinity. So what happens when you remove the magnet? Aren't you changing the flux? So there'll be some EMF induced, and it's a superconducting coil. So something happens, it generates a current inside such that it will maintain the same flux. So the new flux will be L into I. This must be equal to the previous flux. Getting it? So this will be some flux. This is the same flux as before. Now, why this happens, what is all this, we'll not get into it. But this is what a superconductor does. So if it is an advanced paragraph, this is how they'll frame the whole story. Clear with the theory part? So why it does, we're not interested, but this is what a superconductor does. If you try to change the flux, it will try to maintain the flux by inducing a current in itself. So after explaining all this story, now they'll ask you a question. You take two superconducting rings. Self-inductance L, mutual inductance is also L. Initially, this is carrying current I, this is also carrying current I. Coils are very close to each other. So we can say all the field lines from one will enter the other. And that's why M became L. So this is the initial scenario. Now find the work done by the external force to separate the coils to infinity. So they will explain you what is a superconductor thing and they'll frame something of this sort. Let's get this. Right, Om. Nera. Let's see. So initially, what was the flux? If you take flux on any one ring, that will be Li plus Mi. L1 I1 plus M into I2. Luckily here everything is same. So this is Li plus this is also Li. So flux is to Li. Now when you take them to infinity, the current will become I dash. So the flux will be Li dash, but this must be equal to 2Li. So current has actually doubled in both the coils. The initial energy will be just now iso energy in a coupled circuit. Half Li square, half L2I square plus M I1 I2. So that is also L. That will be 2Li square. Whereas in the final energy, half L2Y square, half L2Y square, and so the current in the coils will become double in order to maintain the same amount of flux. So this much work you have to do because this is the increase in energy of the system. Clear? Yeah, that's a bit about the superconductors and the mutual inductance. Any doubts on this? Easy to solve, but you should know the concept. Next thing, transformers. So we are slowly entering into AC circuits now. So what is a transformer? Not the movie wala, it's an electrical transformer. So the construction is pretty simple. It has very few moving parts. One of the most efficient electrical systems. These things have efficiency of around 99.9 and over. If you make a transformer of 99% efficiency, they'll throw you out. So we have an iron core. So we have a winding here, one side. Let this be N1 turns. Let the current be I1 and let the voltage be V1. Let this be I2, let the voltage be V2, and let this be N2 turns. So when the current flows from the left-hand side, these coils will generate a magnetic field. So if you see, an iron core has a very high value of mu, so magnetic field will easily pass through. So if you look at the magnetic field, so an iron core is like a path of least resistance. So there'll be a negligible flux leakage. The field lengths won't go to infinity. So instead of this, if you have taken only simply two coils, you will notice some of the field lengths are entering, but most of them are actually escaping to infinity. So very few field lengths will actually enter the coil. So, and remember what I said, magnetic fields are nothing but a form of energy. So you're actually kind of losing energy there. Now, since the number of, if you see the number of lines are same, the flux through each turn is same. There is a flux leakage here. So whatever is the flux through per coil, it will be the same on the left and the right hand side. Now, if you look at the left hand side, the flux on the coil 1 will be the number of turns N1 into phi. Phi is the flux through each turn. Then we get voltage V1 is nothing but minus d phi 1 by dt. That will be minus N1 d phi by dt. Flux 2 will be N2 into phi. If you divide them, you end up with V1 by V2 is equal to N1 by N2. There, that's our first formula there. This is how the voltage will vary based on the number of turns. If N1 is greater than N2, then we get V1 greater than V2. This is called step down transformer, meaning you can make higher voltage go into lower voltage. If N1 is less than N2, then V1 is less than V2. So the output will be bigger than the input. This is called step up transformer. And similarly, the energy is conserved, assuming 100% efficiency. V1, I1 will be equal to V2, I2. There in transformer, generally, there are two formulas. Power is constant and the voltage will depend on the number of turns. And if you look at this, the input and output will be out of phase by 180 degrees if you keep them in the same sense of rotation, because both are opposing. The field lengths will enter in the opposite direction. So that's the basic idea about the transformer, how it works. So if you actually go back to the beginning of this thing, right? Ever heard about this thing called AC-DC wars? There is a wars. Matlab, literally they used to call that. So this all started right somewhere in late 1800s and 1900s ka time na. And the main guy is the Edison. Edison, right, more than a scientist, is actually more of a businessman. So this guy during in US ka cities mein, right, during night time for the street lightning, you must have seen this old Sherlock Holmes and all that thing. Remember, they used to street lamps, the black thing like a small house kind of thing. So inside you put some oil there and you have a lamp kind of thing, and then that burns and then gives you the light. So that is the street lighting they used to use. And these two, there used to be people who used to get this done. So throughout the night, people used to, keep roaming and, putting oil and making sure everything is on and all. So it is a job. People used to have very weird jobs that time. Few people used to work as alarm clocks. They'll come and wake you up at morning 6 o'clock. They will knock your door. If you're sleeping in the first floor, they'll knock your window with a stick. So this Edison, right, goes to one of the council and he puts a proposal. All this burning oil, putting a lamp, and is all old tech. Why don't we install bulbs in the streets of Chicago? It might look pretty normal to us for now, but during that time, putting bulbs meaning it was something new. Bulbs were pretty recent. And this guy saying we'll put the entire street of bulbs. Just imagine tomorrow BMC telling you we'll have robots from tomorrow cleaning the roads. You would think like, wow, BMC is like so advanced. Something of that sort. And he got a contract. So this guy installed all the bulbs and all, and Edison was in the favor of DC. He was using DC generators. And he was lighting up and everything. People were impressed and all, and he was making a lot of money. Because it is much more cheaper, to run. There's no people involved. Just install the bulbs and they'll keep glowing throughout the night. It actually costs much less, and he was making a lot of profit. And he started taking up contracts in other cities also, and that is when Tesla came. But Tesla was not a scientist, but not a businessman. He was more of a scientist. So, but he had investors and all. So now it has literally become a fight for the contracts. But Tesla entire system was based on AC generators. Bulbs are same, everything is fine, but one guy is using AC and one guy is using DC. And Edison was pissed off because he doesn't care about science, but he is more interested like, yeah, boss, I'm losing my profits. So then they both used to, bid for contracts all over the country and everywhere. Sometimes Edison used to win, sometimes Tesla used to win. And Edison used to have a proper gang and all. So they literally used to go and beat this, Tesla people. They used to break into their offices. They used to kidnap cats and dogs. Used to put AC current and kill them. And used to give publicity. See, the animals died because of AC current. So they were doing all kind of nonsense. Meaning at one point, right, they went so mad. They brought an elephant from an abandoned circus. They kept it on the street, put AC current and killed it live in front of everyone. It was a live execution. They were so mad. So fight was going on, and eventually, right, Tesla, they installed generators near the Niagara Falls. That changed everything because now you're getting power free of cost. DC ka biggest problem was the generator has to be within a distance of 2 kilometers. As the length of the wire becomes more and more, DC generators, right, they started becoming pretty inefficient. You're losing a lot of power in the wire only. Because see, when you're sending through a wire, current I, there is a power, remember, I square R? The transmission wire itself is dissipating energy. So I'm sending you 100 watts. By the time it reaches your house, you're getting only 40. Now the question is, will you pay the bill for 40 or 100? You will say, I'll pay 40. I used 40. But the guy who generated will say, boss, I to generated 100. I want money for 100. So who will pay for the remaining 60? So it becomes pretty costly and everything. But Tesla, right, AC generators did something. And that changed the whole game. These people installed generators in Niagara Falls, which was giving power 24/7, free of cost. And you are having transmission lines from a distance of 200, 300 kilometers. It was a game changer. And then DC generators could not, give you that kind of cost efficiency. And eventually AC won the war. So what was the difference is this. If you try to do the same thing with a transformer, let me see what happens normally. So when you actually do a power transmission right now, this is what actually happens. So you have a power plant. Generally, you don't want to stay near a power plant. If you have a coal-based power plant, 5 kilometers surrounding area will be mess. So generally, these power plants are installed somewhere out of the city, pretty far, 200, 300 kilometers far in a barren lands. So the power plants, they generate voltages up to 2 to 3 lakh volts. Now in India, they're trying to make it 1 million. So you generate pretty high voltages. Then you start sending this power. Now, once this enters the city outskirts, or if you're living in a big society, you will get the line into your society, and then you will have 33 kV kilovolt substations. You must have seen these things. You get 33 kV substations. Then these things go again. Then you get 11 kV substation. Basically, you're using step-down transformers to bring the voltage down. And by the time it reaches your house, you get your 220 volt supply. Again, remember circuit has to be completed. So yeah. Now the problem, imagine you have a power plant 200 kilometers per hour. You are literally using 400 kilometers of wire. No matter how much good copper you use, it will have some resistance. Now, when you take it over for 500 kilometers, that adds up to a large resistance. And if you're sending even half ampere of current, you get a lot of it produced. Now, this is the scenario that will happen. I'll send you 100, you will get 50. You want to pay for 50, but I want the bill for 100. The remaining 50 is gone. Transmission losses will be huge. And this is where DC literally failed. So these transmission wires produce heat. Which is I square R. This R is the resistance of the transmission wire. These are called copper losses. Remember the terminology, huh? It's a pretty good theoretical question. Do you guys remember eddy current losses? Eddy heat losses, that's a different thing. That comes because you get currents are induced in a metallic blocks and you get random current loops. So how does this increase in the voltage help us? Remember, power is V into I. So by increasing the voltage to very high value, current becomes negligible. If current becomes negligible, I square R becomes negligible. That is the catch. So the higher the voltage goes, current will go into microamperes. The transmission wire losses will be negligible. So meaning now we have reached a stage where I send you 100, you get almost 98, 99. That much error is acceptable. So by increasing voltage to high values, we can decrease current. Therefore, this copper losses decrease. Why couldn't we do this with DC? The problem with DC, so if you send a constant current, there will be a magnetic field. So if you look at the flux in the secondary coil, that will be N2 into phi. But remember, this will be constant because I is constant. The flux is not changing. Then when I try to do V2, which is minus d phi 2 by dt, I'll get 0. There'll be no output. DC circuits won't work. In case of an AC, we use something like sine omega t function. So it's changing with time. You get a flux there. So DC does not work in transformers. This is where Edison failed a big time. That transformers changed everything. And then, but anyway, Tesla was a kind of a genius. This guy kind of systems he has, created and made up, right? We still use most of them till today. His designs were so ahead of his time. This went on. AC was winning everywhere. In AC, everyone thought DC was useless. Then came 1950s and 60s integrated circuits. People realized, all these computers and everything that you're using, AC can't be used. They don't work. So if you see, look at your mobile phone. It's a 12-volt charging. DC it is. Right. So all your computing and everything is based on literally DC. So finally we came to a thing, boss, you want transmission, AC is the best. But when you want electronics, DC is the best. So we bring your power to the house in AC, then we use an adapter to convert AC DC. We will see that in semiconductors, how to convert AC to DC. That we used to charge your mobile phones and your everything. Your Mumbai local trains, what kind of motors they run on? They run on DC motors actually. DC motors produce more torque. If you ever see next time, observe your local train. In 12 compartments, there'll be 3 compartments where half of the compartment is sealed. You have these pylons on the top. Observe here, Kabhi. So they get power through AC, 25,000 volts. They convert it into DC, then they run the motors here. You have actually 3 engines for your local train. So one engine is too slow to accelerate. So because local trains will stop and decelerate and accelerate pretty fast, you need more engines. That's a bit about transformers. That's it. There's the 2 main formulas there. V1 by V2 is N1 by N2, and V1 I1 is equal to V2 by I2, and some theoretical ones. DC doesn't work and all that stuff. Let's get these 5 questions. Easy stuff. What is the first one? The core of a transformer is laminated. Isn't that what we do? We laminate it. It is to reduce eddy heat losses. Don't get confused. Copper losses happen in the transmission wire. They don't happen inside the transformer. Hysteresis loss actually happens inside the magnets. It is removed from the portion, but we will discuss a bit later on in bar magnets. And there's nothing called magnetic loss. So the answer is eddy current. So in physics, we have 3 types of losses: copper losses, hysteresis losses, and eddy current losses. Yeah, finish off, get the rest. Power transmission input power 2300 volts, output is 230. So V1 by V2 is equal to N1 by N2. So 10:1 ratio, 4000 to 400. बस वही करना था, 2 formula और कुछ नहीं है. Frequency doesn't change. If you're sending sine omega t and if you differentiate, you get cos omega t. Omega doesn't change. What changes is the magnitudes. So what about this thing? Step-up transformer is 1:8 turn ratio, N1 by N2. 120 volt primary, and this is V1. So we'll get V2 will be V1, which is 120, and 8 by 1, this is the voltage. So I2 will be V2 by R. That is 120 into 8 by 10 power 4, 96 milliamperes. This will be 120 into 8 by 10 power 4. That is 96 by 10 power 3. What is this efficiency? Power output by power input into 100. यहाँ पे transformer to use 140 watt. So power output is 140. Power input is 240 and the current is 0.7. And this is 240 into 0.7. Check it out, how much is that? 20 by 240 into 100. 100 by 12. 25 by 3, 83.33%. And this is 0.05. That's it. Transformers generally don't have much on this. Clear with this? Yes, that's about transformers. And with that, we are done with the chapter. So check it out. We have done almost 38 questions. And if you see the whole chapter, right, there are very few easy questions. Most of them were like elaborate and they had a lot of variations and stuff. So make sure to go through the whole thing. Quite an important chapter. It has a pretty good weightage, just like rotation and mechanics. Right. So okay, on Friday when we catch up, we'll start off with alternating current. It's not a big chapter, right? It's little different, and I'm going to teach you even more differently. We are going to use something like complex numbers to do the chapter. So not much basic stuff, but you'll see it will be a little weird, but I think half an hour after that you'll find it quite easy and comfortable. It is a quite a small chapter. I think we should wrap up that also by next week only. And after that we have waves and wave optics and modern physics. We'll go ahead with that. So try to finish off, EMI, start doing it. Don't delay it anymore. Try to at least wrap up this by next Monday. Take a week's time and start solving. Right. So that way. Okay, with that, we'll wrap up for the day. Right. Do remember there's a test online on MEC and everything. So do make sure to give it. So any doubts in the class notes, any other doubts, you can stay back and ask, right? Or else you're free to leave. So I'll see you guys again on Friday. So take care, stay safe.
Sir,